In 1933, a Swiss astronomer named Fritz Zwicky pointed his telescope at the Coma Cluster, a collection of over 1,000 galaxies hanging in the darkness of space. He was measuring their velocities, calculating how fast they moved relative to one another. And what he found made no sense. The galaxies were moving too fast. Far too fast. According to the laws of physics, the visible matter in the cluster, all the stars, all the gas, all the dust, did not contain enough gravitational force to hold these galaxies together. They should have been flying apart, scattering into the void like sparks from a fire. But they weren't. Something was holding them in place. Something invisible. Something we couldn't see. Zwicky called this invisible substance dunkel materie, dark matter. It was a radical idea, dismissed by many of his peers as speculation, as the error of faulty measurements. But Zwicky was right. And in the decades since, we have come to realize that dark matter is not just present in the Coma Cluster. It is everywhere. It permeates the universe, woven through the fabric of space itself. It does not emit light, does not absorb light. It does not interact with electromagnetic radiation in any way we can detect. And yet, it is there, holding galaxies together, shaping the structure of the cosmos, making up approximately 85% of all matter in the universe. Let that sink in for a moment. Everything we can see, every star, every planet, every nebula, every galaxy accounts for only 15% of the matter that exists. The rest is dark, hidden, unknown. We live in a universe where the vast majority of what is real is completely invisible to us. We can only infer its presence by the way it affects the things we can see, by the way galaxies spin, by the way light bends around massive objects, by the gravitational fingerprints it leaves on the cosmic microwave background, the afterglow of the Big Bang itself. Dark matter does not glow. It does not shine. It passes through ordinary matter, as if it weren't there, ghosting through planets and stars, and even our own bodies, without leaving a trace. And yet, without it, the universe as we know, it would not exist. Galaxies would never have formed. Stars would never have ignited. Life would never have begun. Dark matter is the scaffolding of the cosmos, the invisible framework upon which everything we see is built. And we have no idea what it is. Scientists have proposed dozens of theories. Some suggest that dark matter is made of particles we have not yet discovered, exotic substances that exist outside the standard model of particle physics. Others believe it could be primordial black holes, remnants of the early universe, too small and too dark to be seen, but massive enough to exert gravitational influence. There are theories involving modified gravity, ideas that suggest our understanding of how gravity works might be incomplete. But despite decades of research, despite experiments conducted in laboratories deep underground and observatories scanning the heavens, we still do not have a definitive answer. The search for dark matter is one of the greatest scientific endeavors of our time. Detectors buried miles beneath the Earth's surface wait in silence, hoping to catch the faint signal of a dark matter particle colliding with an atom. Particle accelerators smash protons together at nearly the speed of light, searching for evidence of new particles that could explain the mystery. Telescopes map the distribution of galaxies across billions of light years, tracing the gravitational influence of dark matter on the large-scale structure of the universe. And yet, it remains elusive, a ghost in the machine, a presence felt but never seen. What makes dark matter so compelling is not just the mystery of what it is, but the implications of its existence. If the majority of the universe is made of something we cannot see, something we do not understand, then what else might be out there? What other forces, what other phenomena might be shaping reality in ways we have yet to comprehend? Dark matter challenges our most fundamental assumptions about the nature of existence. It reminds us that the universe is far stranger, far more complex than we ever imagined. And it raises questions that go beyond science. Philosophical questions. Questions about the limits of human knowledge. Questions about what it means to understand the universe when most of it is hidden from view. We pride ourselves on our intellect, on our ability to unlock the secrets of nature. But dark matter humbles us. It shows us that there are mysteries we may never solve, puzzles we may never piece together. And in that humility, there is a kind of beauty, because the universe does not owe us answers. It does not care whether we understand it or not. It simply exists, vast and indifferent, governed by laws we are only beginning to grasp. And dark matter is a reminder of that truth. It is a reminder that we are small, that our knowledge is limited, that the cosmos stretches far beyond the reach of our telescopes and our theories. And yet, we keep searching. We keep asking questions. We keep reaching into the darkness, hoping to find the light. To understand dark matter, we must first understand how we discovered it. The story begins not with a single observation, but with a pattern that emerged over decades, a slow accumulation of evidence that something was wrong with our picture of the universe. Astronomers in the early 20th century believed they had a fairly good grasp of how galaxies worked. Stars orbited around a central point, held in place by gravity. The more mass at the center, the stronger the gravitational pull, and the faster the stars would orbit. This was basic Newtonian mechanics, confirmed by centuries of observation. But then came the rotation curves. In the 1970s, astronomer Vera Rubin began studying the rotation of spiral galaxies, measuring how fast stars moved at different distances from the galactic center. What she expected to find was a simple pattern. Stars close to the center would move quickly, while stars farther out would move more slowly, their orbital velocity decreasing with distance. This is how planets in our solar system behave. Mercury orbits the Sun much faster than Neptune, because it is closer to the Sun's gravitational influence. But that is not what Rubin found. Instead, she discovered that stars at the outer edges of galaxies were moving just as fast as stars near the center. The rotation curves were flat, not declining. This made no sense. Unless there was far more mass in these galaxies than could be accounted for by visible stars and gas, the outer stars should be moving more slowly. The only explanation was that galaxies contained vast amounts of invisible matter, distributed in a halo around the visible disk. Dark matter. Rubin's work was groundbreaking, but it was not entirely new. Fritz Zwicky had proposed the existence of dark matter decades earlier, based on his observations of galaxy clusters. And in the 1960s, astronomer Jan Oort had noted discrepancies in the motion of stars in the Milky Way, suggesting the presence of unseen mass. But it was Rubin's meticulous measurements, her careful analysis of rotation curves, that provided the most compelling evidence. Dark matter was not a quirk of one galaxy or one cluster. It was universal. It was everywhere. The implications were staggering. If galaxies contained this much invisible matter, then the universe was far more massive than anyone had realized. And if this matter did not emit light, it meant that our entire understanding of what the universe is made of was incomplete. The atoms that make up stars, planets, and people, the stuff we call ordinary matter, are composed of protons, neutrons, and electrons. These particles interact with light. They absorb it, emit it, scatter it. But dark matter does not. It is something else entirely. Scientists began to search for candidates. What kind of particle could exist in such vast quantities, exert gravitational influence, and yet remain completely invisible? One early idea was that dark matter might be made of ordinary matter that simply did not emit light. Brown dwarfs, for example, are failed stars, too small to ignite nuclear fusion. Black holes, remnants of dead stars, emit no light. White dwarfs, neutron stars, rogue planets, all of these could, in theory, contribute to the missing mass. These objects were collectively called MACHOs, or massive compact halo objects. But surveys searching for MACHOs found that they could not account for the amount of dark matter needed. There simply were not enough of them. The universe would need to be filled with trillions upon trillions of black holes and brown dwarfs, and there was no evidence for such a population. So scientists turned to another possibility. What if dark matter was not made of ordinary atoms at all? What if it was composed of exotic particles that had never been detected in a laboratory? This led to the development of the WIMP hypothesis. WIMPs, or weakly interacting massive particles, are theoretical particles that do not interact with light or ordinary matter except through gravity and possibly the weak nuclear force. They would be invisible, intangible, passing through solid objects without leaving a trace. And yet, because they have mass, they would exert gravitational influence. They would shape the structure of galaxies. They would hold the universe together. WIMPs became the leading candidate for dark matter, and experiments were designed to detect them. Deep underground, in mines and tunnels shielded from cosmic radiation, scientists built detectors filled with liquid xenon or other materials. The idea was simple. If WIMPs exist, they should occasionally collide with the atoms in the detector, producing a tiny flash of light or a faint signal that could be measured. These experiments have been running for years, waiting for the telltale sign of a WIMP interaction. And so far, they have found nothing. The silence is deafening. The detectors sit in the dark, waiting, listening, hoping for a signal that has not yet come. But the absence of detection does not mean WIMPs do not exist. It could mean they interact even more weakly than expected. It could mean they are lighter or heavier than current experiments can detect. Or it could mean that dark matter is something else entirely, something we have not yet imagined. The search continues. The detectors keep running, and scientists keep refining their theories, exploring new possibilities, hoping that one day they will catch a glimpse of the invisible. Dark matter is not just an astronomical curiosity. It is the foundation upon which the universe is built. To understand why, we must go back to the beginning, to the moments just after the Big Bang, when the cosmos was a hot, dense soup of particles and energy. In those first moments, the universe was smooth, almost perfectly uniform. But not quite. There were tiny fluctuations, quantum ripples in the fabric of space, regions where matter was just slightly more dense than average. These fluctuations were the seeds of everything that would come after. In a universe made only of ordinary matter, these tiny density variations would have struggled to grow. Ordinary matter, composed of protons and electrons, interacts with light. In the early universe, this meant that radiation pressure, the outward push of photons, counteracted the inward pull of gravity. Matter tried to clump together, but light kept pushing it apart. The battle between gravity and radiation slowed the formation of structure. But dark matter changed everything. Because it does not interact with light, dark matter was immune to radiation pressure. It began collapsing under its own gravity long before ordinary matter could. Dark matter clumped together first, forming vast halos, invisible scaffolding that shaped the cosmic web. And as these halos grew, their gravity pulled in ordinary matter, gas that could cool and condense, eventually forming stars and galaxies. Without dark matter, this process would have taken far longer, perhaps too long. The universe might have remained a diffuse, nearly uniform expanse, with no galaxies, no stars, no planets, no us. This is why dark matter is called the framework of the universe. It is the hidden architecture that allowed structure to emerge from chaos. Simulations of the early universe confirm this. When scientists run computer models that include dark matter, they produce a cosmos that looks like our own, a web of galaxies connected by filaments of matter, separated by vast voids. When they run simulations without dark matter, the universe looks nothing like what we observe. The match is too precise to be coincidental. and the evidence extends beyond galaxy formation. Dark matter also explains gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Massive objects warp the fabric of space-time, bending the path of light that passes near them. When we observe distant galaxies, we sometimes see their light distorted, stretched into arcs, or even multiple images. This lensing effect allows us to map the distribution of mass in the universe, including mass that does not emit light. And what we find, again and again, is that there is far more mass than can be accounted for by visible matter alone. One of the most famous examples of gravitational lensing is the Bullet Cluster, a pair of galaxy clusters that collided billions of years ago. When astronomers studied the aftermath, they found that the visible matter, mostly gas, had been slowed by the collision, piling up in the center. But the gravitational lensing, which reveals where the mass actually is, showed something different. Most of the mass had passed right through the collision, unaffected. This was dark matter, ghosting through the ordinary matter without interacting, continuing on its path as if nothing had happened. The Bullet Cluster is one of the strongest pieces of evidence for dark matter. It shows not just that dark matter exists, but that it behaves exactly as the theory predicts. It does not interact with ordinary matter except through gravity. It does not collide. It does not slow down. It is a substance that exists in parallel to the matter we know, overlapping with it in space but never touching. A phantom universe, invisible but ever present. And yet, for all this evidence, we still do not know what dark matter is made of. The WIMP hypothesis remains popular, but it is not the only possibility. Another candidate is the axion, a hypothetical particle first proposed to solve a different problem in particle physics. Axions, if they exist, would be incredibly light, millions of times lighter than an electron, and they would interact even more weakly than WIMPs. Detecting them would require entirely different experiments, one sensitive to the faint signals of axion decay or interaction. There are also more exotic proposals. Some physicists suggest that dark matter could be made of primordial black holes, formed in the first fractions of a second after the Big Bang. These black holes would be tiny, some no larger than an atom, but incredibly dense. They would exert gravitational influence without emitting light, fitting the profile of dark matter. Others propose that dark matter is not a particle at all, but a modification of gravity itself, a sign that Einstein's equations need revision on cosmic scales. This idea, called modified Newtonian dynamics, or MOND, has its proponents, but it struggles to explain all the observations as elegantly as dark matter does. The truth is, we are searching for something we cannot see, using tools designed to detect things that interact with light and matter. It is like trying to catch a shadow. We know it is there, because we can see its effects, but the thing itself remains elusive. And so the search continues, in laboratories and observatories around the world. Each experiment a new attempt to pull back the veil on the universe's greatest mystery. The cosmic microwave background, or CMB, is one of the most important pieces of evidence for dark matter. It is the oldest light in the universe, radiation left over from the Big Bang, emitted when the cosmos was just 380,000 years old. At that time, the universe had cooled enough for atoms to form, and light was finally able to travel freely through space. What we see today, when we map the CMB, is a snapshot of the infant universe, a record of its temperature and density variations across the entire sky. And what that snapshot reveals is extraordinary. The CMB is not perfectly smooth. It contains tiny fluctuations, regions that are slightly warmer or cooler than average. These fluctuations correspond to the density variations in the early universe, the seeds that would eventually grow into galaxies and galaxy clusters. By analyzing the pattern of these fluctuations, scientists can measure the composition of the universe with astonishing precision. And what they find is that ordinary matter, the atoms that make up everything we see, accounts for only about 5% of the universe's total energy content. Dark matter makes up about 27%. The rest, roughly 68%, is something even stranger: dark energy, a mysterious force driving the accelerated expansion of the universe. But that is a story for another time. What matters here is that the CMB gives us a census of the universe, a detailed accounting of what it is made of. And dark matter is an essential component. Without it, the fluctuations in the CMB would not match what we observe. The universe would look different. It would be different. The CMB also tells us something else. It tells us that dark matter must have been present in the early universe, shaping structure from the very beginning. This rules out certain theories. For example, if dark matter were made of black holes formed later in the universe's history, they could not have influenced the CMB. The timing does not work. Whatever dark matter is, it must have existed since the first moments after the Big Bang, woven into the fabric of space from the start. This has led scientists to focus on particles created in the Big Bang itself. In those first fractions of a second, the universe was a cauldron of energy, hot enough to produce all kinds of exotic particles. Most of these particles decayed almost immediately, but some, according to theory, could have survived. If dark matter particles are stable, if they do not decay over time, then the ones created in the Big Bang would still be here today, filling the universe, passing through us even now as we sleep. It is a strange thought. At this very moment, trillions of dark matter particles could be streaming through your body, through the walls of your room, through the Earth itself, completely undetected. They do not interact with the atoms in your cells. They do not scatter off the molecules in the air. They simply pass through, like ghosts. Their only influence the faint tug of gravity they exert on everything around them. We are swimming in an ocean of dark matter, and we do not even notice. And yet, despite this constant bombardment, we have never definitively detected a single dark matter particle. The experiments designed to catch them are among the most sensitive instruments ever built. They sit deep underground, shielded from cosmic rays and other sources of background radiation, waiting for the rare event when a dark matter particle might collide with an atom in the detector. The collision, if it happens, would produce a tiny flash of light or a faint vibration, a signal so small that it requires years of data collection to distinguish from noise. Some experiments have claimed tentative detections, brief anomalies in the data, signals that could be dark matter or could be statistical flukes, but none have been confirmed. The scientific standard for discovery is high, requiring not just one detection, but reproducible results, signals that appear again and again, independently verified by multiple experiments. And so far, dark matter has not crossed that threshold. It remains a hypothesis, supported by overwhelming indirect evidence, but lacking the final, definitive proof. This has led some scientists to wonder if we are looking in the wrong place. If dark matter interacts even more weakly than we thought, our detectors might never catch it. Or if dark matter is made of particles far lighter or heavier than expected, current experiments would miss them entirely. The parameter space, the range of possibilities, is vast, and we have only explored a small corner of it. There is still so much we do not know, but the search is not futile. Every experiment that comes up empty narrows the possibilities. Every null result tells us something about what dark matter is not, even if it does not tell us what it is. Science proceeds by elimination, by ruling out hypotheses one by one until only the truth remains. And in that process, patience is essential. The answers will come, but they will come slowly, through years of careful work, incremental progress, and the occasional breakthrough. The universe has kept its secrets for billions of years. A few more decades of searching is nothing in comparison. One of the most intriguing aspects of dark matter is how it shapes the visible universe. Galaxies are not scattered randomly through space. They are organized into a vast, intricate structure called the cosmic web. Imagine a sponge with dense filaments and sheets separated by enormous voids. That is what the universe looks like on the largest scales. Galaxies cluster along these filaments, like beads on a string, while the voids remain nearly empty, vast stretches of space where almost nothing exists. This structure is a direct result of dark matter. In the early universe, dark matter began collapsing under its own gravity, forming clumps and halos. These halos attracted ordinary matter, which cooled and condensed, forming stars and galaxies. Over billions of years, gravity continued to pull matter together, but not uniformly. Some regions became denser, while others became emptier. The result is the cosmic web, a pattern that emerges naturally from the distribution of dark matter. Computer simulations of the universe's evolution reproduce this structure with stunning accuracy. Scientists input the initial conditions, the density fluctuations from the CMB, and let gravity do the rest. The simulations show dark matter collapsing into filaments and nodes, with galaxies forming at the intersections. When these simulations are compared to actual observations of the large-scale structure of the universe, the match is nearly perfect. This is one of the strongest confirmations that our understanding of dark matter, while incomplete, is fundamentally correct. But the cosmic web also reveals something else. It shows that dark matter is not just passively holding galaxies together. It is actively shaping the evolution of the universe. The distribution of dark matter determines where galaxies form, how they grow, and how they interact. When two dark matter halos collide, they can trigger bursts of star formation, fuel supermassive black holes, and even create the conditions for life. Dark matter is not just background. It is a dynamic, evolving component of the cosmos. And yet, for all its influence, dark matter remains invisible. We can map its distribution using gravitational lensing by observing how it bends light from distant galaxies. We can infer its presence from the motion of stars and gas, but we cannot see it directly. It is a presence defined by absence, a substance known only by its effects. This makes studying dark matter both frustrating and fascinating. We are like detectives trying to solve a crime, where the culprit leaves fingerprints but no other trace. One of the tools scientists use to study dark matter is galaxy clusters. These are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, vast clouds of hot gas, and enormous amounts of dark matter. By measuring the temperature and distribution of the gas, astronomers can estimate the total mass of the cluster. And what they find, again and again, is that the visible matter accounts for only a small fraction of the total. The rest is dark matter, holding the cluster together. The gas in these clusters is so hot that it emits X-rays, which can be detected by space-based telescopes. By mapping the X-ray emission, scientists can create a picture of how mass is distributed in the cluster. And when they combine this with gravitational lensing data, which shows where the dark matter is, they get a complete view of the cluster's structure. What emerges is a picture of dark matter halos, vast and diffuse, surrounding and interpenetrating the visible galaxies and gas. Some of the most detailed studies of dark matter come from merging galaxy clusters. When two clusters collide, the visible matter interacts, heats up, and slows down. But the dark matter, which does not interact with ordinary matter except through gravity, passes right through, barely affected by the collision. This creates a separation between the visible and dark components, a smoking gun for dark matter's existence. The bullet cluster mentioned earlier is the most famous example, but there are others. Each one provides further confirmation that dark matter is real, that it behaves as predicted, and that it is essential to understanding the universe. But these observations also raise new questions. If dark matter does not interact with itself, why do we see such a smooth distribution? Ordinary matter clumps together because particles collide, lose energy, and settle into dense structures. But dark matter, if it truly does not interact, should remain more diffuse. Yet simulations that assume dark matter is completely collisionless sometimes produce structures that do not quite match observations. Could dark matter have a small, previously unknown interaction? Could there be a dark force, analogous to electromagnetism, acting only on dark matter particles? This idea has led to the concept of self-interacting dark matter, or SIDM. In this model, dark matter particles occasionally collide with one another, not with ordinary matter, but with themselves. These collisions would be rare, but they could smooth out the distribution of dark matter in the centers of galaxies, solving some of the discrepancies between simulations and observations. It is a speculative idea, but it is being taken seriously, and experiments are being designed to test it. The universe, it seems, is never as simple as we would like. Every answer leads to new questions. Every piece of the puzzle reveals edges that do not quite fit. And dark matter, the invisible framework of the cosmos, is at the heart of these mysteries. There is something deeply unsettling about the idea that most of the universe is invisible. We are creatures of light. Our eyes evolved to detect photons, to see the world in colors and shapes and shadows. Our telescopes extend our vision, allowing us to peer across billions of light years, to see galaxies as they were in the early universe. But all of this, all of our observations, all of our understanding is based on light. And dark matter does not emit light. It does not reflect it. It does not interact with it in any way. This means that we are essentially blind to the majority of the universe. We can infer its presence. We can map its distribution. We can measure its effects. But we cannot see it. And this raises a profound question. What else might be out there, invisible to us, shaping reality in ways we do not yet understand? If dark matter can exist undetected for billions of years, what other phenomena might be lurking beyond the reach of our instruments? Some scientists have proposed that dark matter could be just the tip of the iceberg. If there are particles that do not interact with light, why stop at one type? Perhaps there is an entire dark sector of physics, a whole family of particles and forces that exist in parallel to the standard model, but never touch it. These particles would not just be invisible, they would be completely isolated from ordinary matter, interacting only with themselves. A shadow universe, overlapping with ours, but forever out of reach. This idea, while speculative, is not as far-fetched as it might seem. The standard model of particle physics, which describes all the known particles and forces, is incomplete. It does not include gravity. It does not explain dark matter. It does not account for the matter-antimatter asymmetry in the universe. And it contains parameters that seem finely tuned, as if set by hand, with no deeper explanation. Many physicists believe that the standard model is not the final word, but a low-energy approximation of a more fundamental theory. If such a theory exists, it could include dark matter as a natural component. Some theories, like supersymmetry, predict the existence of entirely new families of particles, some of which could be stable and massive enough to account for dark matter. Others, like string theory, suggest that extra dimensions of space could harbor particles and forces we have never encountered. These ideas are elegant, but they remain unproven. The experiments needed to test them are at the edge of what is currently possible, and in some cases, beyond it. But even if we never detect dark matter directly, its presence is undeniable. The universe we observe, with its galaxies and clusters and cosmic web, cannot exist without it. Dark matter is woven into the fabric of reality, as essential as space and time. And this leads to a strange realization. We live in a universe that is mostly unknown. Most of what exists is hidden from us, accessible only through inference and mathematics. And yet, we continue to search. We continue to ask questions. We continue to reach into the darkness, hoping for a glimpse of the truth. The search for dark matter is not just a scientific endeavor. It is a philosophical one. It forces us to confront the limits of our perception, to acknowledge that reality is larger and stranger than we can directly experience. And in that confrontation, there is a kind of humility. We are not the center of the universe. We are not even made of the same stuff as most of it. We are a small, bright anomaly in a cosmos dominated by the invisible. And yet there is also hope, because the history of science is a history of revealing the hidden. We cannot see atoms, but we know they exist. We cannot see radio waves or X-rays, but we have learned to detect them. We cannot see the curvature of space-time, but we have measured it with exquisite precision. Dark matter is just the latest in a long line of invisible phenomena that we have learned to understand. And there is every reason to believe that one day we will understand it too. The question is not whether we will find the answer. The question is when, and what we will discover along the way. Because the search for dark matter is not just about finding a particle or confirming a theory. It is about expanding the boundaries of human knowledge, about pushing into the unknown and bringing back new insights, new questions, new mysteries. It is about the journey as much as the destination, and that journey is far from over. In the depths of abandoned mines and beneath mountain ranges, scientists have built some of the most sensitive detectors ever conceived. These are not telescopes pointed at the sky. They are instruments buried deep underground, shielded from the constant rain of cosmic rays that bombard the Earth's surface. Their purpose is singular: to catch a dark matter particle in the act of interacting with ordinary matter. And they have been running, in some cases, for decades. One of the most well-known experiments is the Large Underground Xenon Experiment, or LUX, located nearly a mile underground in a former gold mine in South Dakota. The detector consists of a tank filled with ultra-pure liquid xenon, cooled to a temperature just above its freezing point. The idea is simple. If a dark matter particle passes through the xenon and collides with a xenon nucleus, it will cause the nucleus to recoil, producing a tiny flash of light and a small electrical signal. These signals are detected by sensors surrounding the tank, and sophisticated algorithms analyze the data to determine whether a collision occurred. But the signals are incredibly faint. A single dark matter interaction would produce a flash of light equivalent to a handful of photons, barely distinguishable from the background noise of the detector itself. This is why the experiments are so deep underground. Cosmic rays, high-energy particles from space, would create similar signals, overwhelming any potential dark matter detections. By burying the detectors deep beneath the Earth, scientists can shield them from this background radiation, reducing the noise and increasing the chances of detecting a true dark matter event. And yet, after years of operation, experiments like LUX have not detected a single confirmed dark matter particle. The detectors sit in the dark, waiting, recording every interaction, every photon, every electron, and time after time, the signals they detect can be explained by other sources. Radioactive decay in the materials of the detector, neutrons from the surrounding rock, residual cosmic rays that somehow penetrated the shielding. Dark matter remains elusive, but the absence of detection does not mean the experiments are failures. Each year of operation, each improvement in sensitivity, each refinement of the analysis narrows the parameter space. It tells us what dark matter is not. If WIMPs exist, they must be lighter or heavier, or interact more weakly than previously thought. And this information is valuable. It guides theorists, helping them refine their models and propose new candidates. It shapes the design of future experiments, which will probe different energy ranges, different interaction types, different possibilities. Some of the newer experiments are exploring the possibility that dark matter is much lighter than originally thought. Axions, for example, are theoretical particles that could be millions of times lighter than an electron. Detecting them requires a completely different approach. Instead of looking for collisions, scientists search for the faint signals produced when axions decay or interact with magnetic fields. Experiments like a DMX, the Axion dark matter experiment, use powerful magnets and ultra-sensitive detectors to search for these signals, scanning a range of masses one narrow band at a time. The process is painstakingly slow. Each frequency range takes months to search, and the total range of possible axion masses spans many orders of magnitude. It could take decades to complete a full scan. But the scientists are patient. They understand that discovery is not a race. It is a careful, methodical process, one step at a time, one measurement at a time. And somewhere in that vast parameter space, the answer might be waiting. There are also experiments searching for dark matter in space. The Alpha Magnetic Spectrometer, or AMS, is a particle detector mounted on the International Space Station. It analyzes cosmic rays, looking for unusual patterns that could indicate dark matter annihilation or decay. When dark matter particles collide with each other, they could, in theory, annihilate and produce ordinary particles like electrons and positrons. These particles would create a distinctive signature in the cosmic ray spectrum, a signal that AMS is designed to detect. And there have been hints. In 2013, AMS reported an excess of positrons at certain energies, more than could be explained by known sources like pulsars or supernova remnants. Could this be dark matter? It is possible. But it is also possible that the excess comes from some other, more mundane source. The data is tantalizing, but it is not conclusive. More observations are needed. More analysis. More time. This is the reality of dark matter research. It is a field defined by patience, by incremental progress, by the slow accumulation of evidence. There are no sudden breakthroughs, no eureka moments. Just years of careful work, punctuated by occasional hints and puzzles, always with the understanding that the answer may be just around the corner, or it may be decades away. But the scientists persist, because the question is too important to abandon, because the universe deserves to be understood, and because, in the end, the search itself is a kind of answer. Beyond the laboratory, dark matter has captured the public imagination in ways few scientific concepts have. It appears in science fiction, in novels and films, where it becomes a source of mysterious power or a gateway to other dimensions. It features in conspiracy theories, where it is linked to secret government experiments or hidden alien technology. And it has become a symbol, a metaphor for the unknown, for the hidden forces that shape our lives and our universe. Part of the appeal is the name itself. Dark matter sounds ominous, mysterious, almost supernatural. It evokes images of shadows and secrets, of things lurking just beyond the edge of perception. And while the scientific reality is less dramatic, dark matter is simply matter that does not emit light, the metaphor resonates. We live in a world where so much is hidden, where the forces that shape our lives, from economic systems to psychological drives, operate largely unseen. Dark matter becomes a stand-in for all of these invisible influences. But there is also a deeper connection. Dark matter reminds us that our senses are limited, that what we perceive is only a fraction of what is real. We are surrounded by electromagnetic waves, radio, infrared, ultraviolet, that our eyes cannot detect. We are bathed in neutrinos, ghostly particles that pass through our bodies by the trillions every second without leaving a trace. And we are swimming in dark matter, an invisible ocean that we can only infer through its gravitational pull. Our everyday experience is a thin slice of reality, and dark matter is a reminder of everything that lies beyond. This has philosophical implications. If the majority of the universe is made of something we cannot see, something we do not understand, then what does that say about the nature of knowledge? Are there truths that are fundamentally inaccessible to us? Mysteries that will never be solved? Or is it simply a matter of time and technology, of building better instruments and asking better questions? These are not idle musings. They go to the heart of what it means to be human, to seek understanding in a cosmos that does not easily yield its secrets. Some philosophers have argued that dark matter is a kind of modern mystery, comparable to the great metaphysical questions that have occupied thinkers for millennia. What is the nature of existence? What is the relationship between the seen and the unseen? These questions have no easy answers, and dark matter fits neatly into that tradition. It is a scientific problem, yes, but it is also a reminder that the universe is fundamentally strange, fundamentally unknowable in certain ways. And yet, science does not give up. It does not accept the unknowable as final. It assumes that with enough effort, enough ingenuity, enough time, the mysteries can be solved. This optimism, this faith in human reason is what drives the search for dark matter. It is the belief that the universe, however strange, is governed by laws, and that those laws can be understood, that the invisible can be made visible, if only we look hard enough. But there is also a kind of beauty in not knowing. In the mystery itself, the universe does not owe us answers. It does not care whether we understand it. It simply exists, vast and indifferent, unfolding according to its own logic. And there is something humbling, something almost sacred, about confronting that vastness and acknowledging our smallness within it. Dark matter is a reminder that we are not the center of the universe, that there are forces at work far beyond our control, far beyond our comprehension. And in that humility, there is also wonder, because the fact that we can even ask these questions, the fact that we can build instruments to probe the invisible, the fact that we can piece together clues and construct theories and test them against observation, this is extraordinary. We are a species that evolved on a small planet, under a single star, in a galaxy among billions. And yet, we have learned to read the light from distant galaxies, to decode the structure of the cosmos, to infer the presence of things we cannot see. That is a kind of magic, a testament to the power of human curiosity and ingenuity. Dark matter is a challenge, but it is also an invitation to keep exploring, to keep questioning, to keep reaching into the unknown. Because even if we never find the final answer, even if dark matter remains a mystery for generations to come, the search itself is worthwhile. It expands our understanding. It pushes the boundaries of what is possible. And it reminds us that the universe is still full of wonders, still full of secrets, still full of things we have yet to discover. As we continue to search for dark matter, the landscape of possibilities is shifting. New theories are emerging, new experiments are being designed, and the boundaries of what we know are constantly being redrawn. One of the most exciting developments in recent years is the idea that dark matter might not be a single type of particle, but a whole family of them. Just as ordinary matter comes in many varieties: electrons, protons, neutrons, quarks, dark matter could be equally diverse. This idea, sometimes called the dark sector hypothesis, suggests that there could be an entire hidden world of particles and forces, interacting with each other, but not with ordinary matter. These particles could form structures, perhaps even dark atoms,